sometimes her games don't totally make sense. So we're going to talk about probability models today. I've posted 16.6, so you can go ahead and work on it if you want to. It is not required right now. That'll be tomorrow's homework, and we'll maybe have some class time to work on that. We lost some class time today, so I don't know how much we'll get, how much extra we'll get. But okay, so you're standing by the street, not on the street. Don't play in traffic. You're standing by the street, and your friend says, all right, we're going to play a game. Every time a car passes, I get a point. Every time, every time a truck passes, you get a point. And she says your probability is 1 out of 2. Well, okay, cars, trucks, we're talking about 2 different things. But is the probability of a truck passing really 1 out of 2? Is it 50%? Thomas?
Well, it depends on where you are. It's more likely if it's a highway, it's less likely if it's just in your neighborhood.
What are you basing that off of?
Like, personal knowledge? Yeah, personal knowledge.
So you're thinking also, I believe, if I'm inferring correctly, you're talking about like semi-trucks too, like big trucks?
Yeah.
And that's why you're saying it's more likely if you're on the highway? So but you're saying it's not a 1 out of 2, right?
Yeah.
Anyone think it is a 1 out of 2, a 50% chance?
I have something to say against
Okay.
the 1 out of 2.
Argument.
Yeah, the 1 out of 2, it's not really, that's theoretical, not experimental, and we're actually doing it. It's not just an idea.
I would kind of agree with that. I can agree with the fact that we have 2 possible outcomes that we're tracking, and I am one of them. But your theoretical has to be based off math. And it's not like a die where we know there's 6 outcomes and they're all equally likely. To say this would be a 1 out of 2, cars and trucks have to be equally likely to happen. Eli?
I think it mostly depends on the manufacturing of cars and trucks, like how many there are in general.
Ooh, so if we knew the data on how many exist, then we could make some predictions based off that. But still, would the number that exists determine how many are on the road that you're watching? No. So that'd still be a loose relationship. So no, this is not a good game. This is not fair. I didn't mean to pull up the solution page. This is not at all a true probability based off just her saying it. Now, if we sat there for like an hour, watched traffic come by, count the cars, count the trucks, compare those values, then I could make a statement relating the probability of a truck passing versus a car passing. But just saying it's 1 out of 2, nah, that's not true. You need better friends. Or smarter friends, at least. Or friends that aren't trying to cheat. Maybe she knew that and she was just trying to cheat. So, a probability model. What is it when we talk about a probability model? Well, a model is just anything that we use to represent something else. So when I say, say we split up into 2 teams, boys and girls, and I say we're going to play a game, and I'm going to flip a coin to determine who goes first, heads versus tails. Now, am I trying to choose heads versus tails? No, what am I trying to choose between? Boys versus girls. Why would I choose a coin to choose boys versus girls? Brianna?
Because there's 2 sets of, there's heads which could go for girls and tails which could go for boys, so
Yeah.
there's like even and out.
So there's 2 outcomes that I can match up to the 2 outcomes that I'm trying to track. So a probability model is what we're going to use to represent in a situation where we have to make a choice. It doesn't actually have to be what we're talking about. I'm not trying to choose between red and blue here. Maybe I'm just trying to choose between 2 objects where one is more likely than the other, because here, which is more likely, red or blue? Red. As you can see on your paper, and as you see up here, the probability of red, there are 3 chances out of the total 5, versus blue only has 2 chances out of the total 5. Now, what if my slices were not equal? What if I saw a spinner made like this, 3 slices red, 2 slices blue, but what if they were not the same sizes? Would that create issues, Thomas?
It would create issues. It just makes it like there's I don't know how to say it.
So if I cut my slices right here where I showed this, it
would be the same chance if you cut them, but it would be a different chance.
So now would I count 1, 2, 3, 4 out of a total 5, 6, 7, 8? So now is this a 4/8 chance of blue?
Yep. Now it's even.
Is my blue even to my red?
No.
So if I'm going to count slices, I'm only talking about this so you guys know to be careful when you see things like this. If I'm going to count slices, I have to equate them all to the same size. So if I were going to use my half slices, I would need to look at everything as half slices. So instead of 4 out of 8, if I cut this in half and this in half also, now I have a total 10 slices. So I get 4 out of 10, which can reduce to my 2/5, which matches back up with the original. So even if you have to manipulate what you're looking at, you got to make sure that your outcomes are equally sized. By the way, so that you're reminded 10 different times today, Columbus money, New Albany money.
Wow.
Chicago,
What's the
Florence.
probability of that? Oh, come on now. This is getting ridiculous.
So, have you ever been in the car or traveling somewhere or doing something where you think like, man, I just got really lucky? Like once you guys start driving, if you catch all green lights, if you're on your way somewhere and you get all green lights, you're like, man, that was like, what are the chances of that? What does it really mean when somebody, like he said, what's the probability of that or what are the chances of that? Why do we use phrases like that?
Because it's a really small probability that'll happen, and it's just you're really lucky for that to happen.
Yeah. Every light that I go through, it has a chance of being red or green or for a moment yellow. So every light I go through, I have a chance of having to stop. So every light I add into my equation, if I've gone through 3 lights or 4 lights or 5 lights or 6 lights now or 7 lights, and I'm catching all green lights, every light had a chance of stopping me, and if none of them did, I'm thinking to myself, man, one of these lights is going to have to stop me eventually because the probability, but if I keep getting green lights, I'm getting like luckier and luckier because my probability is very, very small. I was watching a video for one of my professional development things last night. He was talking about the difference in effectiveness rates of doctors who are 99.5% effective versus 99.95% effective. And you might think, well, okay, the 99.5, that's pretty darn effective. I'll take that, doctor, right? They're only ineffective half a percent point, 0.5%, 1 out of every 200. Okay, well, so 1 out of every 200 patients, maybe we say surgery doesn't go successful. I don't want to say die. That's not a good thing. So we'll say their surgery isn't successful. But 99.95, still very close to 100. But now, or sorry, this is not 1 out of, yeah, it is 1 out of 200 because it's 0.5%. But what is this? How many of these patients would we expect to, like, if they're 99.95% effective?
Maybe 1 out of 1,000, maybe?
Because I move a decimal place, this is now like 1 out of 2,000, essentially.
Close enough.
So when you're comparing, even though this is very, very, very likely to go successful, you still have a chance of unsuccessful. This, very, 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 very high chance of being successful, but there's still a chance of being unsuccessful. So be careful that when we discuss probabilities, even if it's close to 100, it can be extremely likely, but still it could not happen. Like Lainey in the afternoon class. If you haven't heard, Lainey picked my card accurately and won the entire bag of suckers. She had a very small chance, 1 out of 52, which isn't that tiny, but it's still very small. It was awesome. So we use models. Sorry, longer.
What were the chances of when you're driving to a place it's all green and then on the driving back it's all red?
I mean, we could compute that, but it would depend on how long the light is green versus red. So if we assume a standard, like if we assume the light is green as long as it is red, then we could say that every light you're catching, you have a 1/2 chance. So we would, every new light that I catch would multiply. So I had 1/2 chance of getting that light green, then 1/2 chance of getting that light green, then 1/2 chance of getting the next light, and 1/2 chance. But then by the end of it, when I multiply all these together, my denominator gets very, very big. So your chances combined, 4, 8, 16, 32. So now you'd have a 1/64th chance of that having happened.
With all reds.
Yeah, so then you'd keep compiling the percentages. If they're equal, though. That would have to be like equal red and green. So on your handout, this is kind of hard to see. All these cards are supposed to represent is 1, 2, 3, 4, 5, 6. Notice there are 1, 2, 3, 4, or 5, or 6. So list 1. What's the probability of fewer than 3 shapes? Well, how many have fewer? So that means we cannot count 3. So we have 2 out of 6, or 1/3. Probability of at least 3 shapes. Bless you. At least. Does at least include 3? Yeah, so now this one is these 4 or 2/3. Now, what do you notice about the 1/3 and the 2/3? Especially if you look at how I color coded this. What do you notice about the cards that are circled or blocked out? Bella?
They are reduced. So
Yeah, my fractions are reduced. Let's do another. Hold on. I know you might get it, but I'm trying to push more people to get it. So probability of a fish. Here's my fish, and here's my fish. So 2 out of 6, or it reduces to 1/3. Probability of an apple. If green's gonna work. Nope, there, yep, maybe. Here's some apples, and here's an apple. So I'd get 3 out of 6, or it reduces to 1/2. Probability of a leaf. Here's my leaves. So 1 out of 6, and it can't be reduced. Again, what do you notice about my cards?
If you add them all up, they add up to 1.
If I add all my probabilities, they total 1. Why is that?
Because it's all the chances, so it's 100% probability.
It's used every possible outcome, and each outcome type has only been used once. Notice that none of my cards got circled more than once, but each of them did get circled once. So when we talk about all of the outcomes in a probability situation, it always has to total up to 1. So make sure we recognize that when we talk about every outcome situation possible, it has to total up to 1. And then if we look at list 3, an even number of apples, well, 2 apples and 6 apples.
You forgot 4.
Huh?
You forgot 4.
That's not apples, those are fish. I know it's hard to see. Or an odd number of apples. What do you notice about these probabilities? 1/3 and 1/6. Do they add up to 1? No. They don't equal 1 because did I count or include every possible outcome? No, I've only included a couple outcomes. So if I add these up, yeah, they would actually add up to 1/2 because I have looked at half of the outcomes. Does that make sense? Why our probability has to add up to 1? So, which probability statement would we add to each list to make it completely, or to make a complete probability model of this action? So we need to figure out what is my list missing to make it add up to the 1. So here's our team. We've got our robotics team. So this is fairly relative to us because we have our national champions robotics team. So we've got boys and girls, varying ages. List 1 shows the probability of a boy is 3/5. What probability statement could I put into that list to deal with the rest of the possible outcomes and make those probabilities combine to 1? List 1 is easier. List 2 gets a little bit harder. What am I missing from list 1? So if I look at the probability of being a boy, I've included this guy, this guy, this guy, this guy, this guy, and that guy.
You missed.
Did I miss one? No, I didn't.
No.
So we've got 6 out of 10, or that reduces to 3/5. Layla?
No, you're missing the probability of a girl.
Yeah, we're missing the probability of choosing a girl. So on your paper, write P of girl, probability of girl, in the parentheses. Or P of G, but sometimes you just want to write it out. What's the probability of choosing a girl? I don't even have to count or do any math. Well, okay, do any math. I do have to do a tiny bit of math. Layla, do you know what it is?
2 out of 5.
2 out of 5. I know that since the probability of picking a boy is 3 out of 5, the probability of picking a girl deals with all of the rest of the outcomes. It will be the complement, or it will make it add up to 1. Complementary angles, remember they make a perfect right angle. Complementary probabilities add up to 1. They deal with every possible outcome. Eli?
So it only works if you use everything.
Yeah, it only works if I know that I've included every single possible outcome. So, boys and girls, those are the only 2 types that we're looking at in list 1. But notice that list 2 uses probability of being younger than 12, probability of being 12. So then when we think about what other probability am I missing, well, I've got age younger than 12, age at 12. Ethan?
Older than 12.
Yeah, probability of older than 12. So we could say P older than 12. And if younger than 12 was 3/10, at 12 was 3/10, what will be my older than 12? 4/10 or 2/5. Excuse me. Because I know that these 2 add up to 6/10. So I know that I have to be the complement of that, which is 4/10. Any questions on what we're doing? Nada? None? Zip? Zilch? 0? So, why is this list of probabilities not complete? Take a moment to analyze it. Figure out what we would need to make a complete list. Or, it can also not be a complete list if things overlap. If something gets counted more than once, your probability list won't add up to 1. Nobody new? Let's see, guys. We've already talked. Ooh, Cassidy, we haven't talked yet today.
I didn't raise my hand.
Oh, that was totally him. Emma, was that a hand or was that a stretch? Ooh, Brennan.
For red. Oh yeah. Yeah, for red. There's an odd number in red.
Ah, so if we're looking at red and then we're looking at odd, this is red and odd. It happens in both of those situations.
And same with 1.
And the same with 1.
Oh yeah.
So this gets counted for 2 of these 3, and it gets counted, this was really 4 out of 8. That gets counted for 2 of those 4. It cannot be in multiple locations if I'm looking for a complete list. These probabilities are true, and they're fine. I'm allowed to discuss that. I just will not end up making a complete list because I've counted something more than once. I've got it in 2 different groups. Oriana?
Also with odd and yellow, then there's a 5.
Thank you. Yellow and odd. 5 falls in as one of the odds, and your 1 yellow, it's in both places. Yeah.
Wait, so what you were asking us is, like, how could we make this complete?
No, why is this one not complete?
Okay.
But do you know, like, what probabilities could you use to make a complete list? Like, if we wanted to say, okay, I'm going to make a new list of probabilities, and I want to make a complete one. What are some probabilities that we could look at to make a complete list where it would add up to 1?
I would take out the odd and just put in all the colors, or just put in all the.
So you would do probability of red, probability of blue, and probability of yellow? If I look at these, will any of these overlap with each other? Will any outcomes fall into multiple probabilities? No. My red would be 3/8, my blue would be 4/8, and my yellow would be 1/8. And that would add up to 1. Orion?
Could you do, like in the parentheses, red odd, red even?
Yeah, you could.
Okay.
Yeah, we could get real specific if we wanted to.
Okay.
Come on. We'll get through this. What's it mean to be uniform? Somebody tells you got to wear your uniform, or your team has uniform, or this is a uniform policy. Huh? The same for all. Uniform really means the same for all. So, a probability model where all of my probabilities have equally likely outcomes, that is what we call a uniform probability model. So, what are some situations that we've talked about that are uniform probability models? Think about our lab last week. Isaiah?
We all did the same thing.
Yeah, but so what probabilities every outcome is equally likely to occur? That's what I'm asking. What events were you doing that would have equally likely outcomes for every single one, theoretically at least? Eli?
Everyone?
What do you mean, everyone?
I mean, the coin.
A coin flip. Were you equally likely to get red versus yellow? Theoretically. Yeah. You had a 50-50 chance. Ethan?
Die.
The die roll. Were you equally likely to get any of those numbers on there? Was 1 equal chance of 3, equal chance of 5, equal chance of 4? Yeah, they're all equally likely. Crystal? Yeah, getting red or black, you have another 50-50 chance with a card deck. Orion?
Would the marbles count? Or?
That was not a uniform probability because the chances of the outcomes occurring, when you looked at it and did the theoretical, one of them was like 3 out of, was it 8 or 10 total? 10, right? So my blue was 5 out of 10. My yellow was 3 out of 10. My green was 2 out of 10. So those aren't uniform because they all have different probabilities. But if I changed the marbles in the jar, I could make it have uniform probability. So one thing that we often ask ourselves is, can I use theoretical probability to make predictions? If we cannot use theoretical probability, the main reason we would not be able to use theoretical is, it's fine, she's in the movie, she'll get it later. The main reason we would not use theoretical is if it is not a uniform probability. So can you think of a situation that would not have uniform probability?
Which way?
You know the rules.
Really?
So this is an
Right.
interesting game.
Right, it is then.
One of your boards.
I don't know how we are ever going to get to the park at this rate.
So they've got 3 pieces of paper, and they're walking around. This is seriously, if you get bored over the summer, this seems interesting. You could explore your neighborhood. Every intersection they get to, they pull a piece of paper, and they either go left, straight, or right. I think it'd be funny if they also had a turnaround option.
That would be great.
So we've got 2 situations here. So situation B is your friend's game. Situation A is the city planner wants to know the probability that the car waiting at the stop sign will turn left, go straight, or turn right. So discuss for a moment if situation A is a uniform probability and if situation B is a uniform probability. Are the outcomes equally likely? Can we use theoretical probability to discuss this situation? So take about 60 seconds. Write your answer, chat with people around you, you can do whatever. And I also just got to get these passed out. Tests that I've had for a while. Yeah, I know. I've had them ready to pass out. I just keep forgetting.
Yay.
I know, but finally I remembered.
I got all three by then. I got all of them. All of them I got messed
These chapter 14 tests, the sampling ones are revisions. Just correct your mistakes.
Oh, one's your present. That's the report.
Oh
So I hear Zach and those guys talking about the math, but I don't hear everybody talking about the math.
yeah, they're all the same. I think because there's only 3 options, so it would be
Yo,
What sports did you play?
me, I played soccer up until high school. Then I was in marching band and could not do both. Although I was supposed to be able to do both, but the coach was a jerk, so forget him. Then I swam, and then I played tennis. And I was in like every music group that we had. I was in the jazz band and the concert choir, the chamber choir. Yeah, I was in like.
Yay, I got sample. Did you get that? I want to see how many I got wrong.
Yeah, I got more from just.
I got 3 of them wrong.
Sorry, I was looking at that and then handed you the wrong.
I got 3.
I got the
All right, I want to hear from some people who had good conversations. Who's got some info for me? Is this uniform problem? So let's talk about situation A first. Let's talk about situation A. The city planner is trying to determine they should put a stop light there. So, or a stop sign. Sorry, there is a stop sign. The stoplight is like the next problem. Is it a uniform probability? Is it an equally likely chance that a car will go left, go straight, or go right? Sorry, Ethan, you maxed out for today. Zach, you guys were having a good conversation. What were you talking about back there?
I think it's uniform because, like, it's 1/3 chance each way, right?
So there's 3 outcomes. I agree with you. Is every outcome equally likely to occur is the question we have to kind of argue with here. So do we know what's left down the street?
No.
Do we know what's straight? Do we know what's right? So what if left was a neighborhood, right was a parking lot, and straight was a school? Huh? Or more highways or something. If we knew the outcomes, if we knew where those streets were going, we could better predict this. We don't know anything about where those streets are headed.
Or who's the person in the car.
Or who, and this would be talking about every car. So because this is unique to who's driving, where they're going, what they're trying to accomplish, this would not be uniform. Because if left goes into a neighborhood and right goes out to the highway, it's going to be a lot more likely that cars are headed to the highway than into the neighborhood because there's going to be less people living in the neighborhood. Less of the community would need to go into a school versus a shopping market, like a grocery. So we need to know where they're headed, but we don't. We don't know the info, so it's not uniform. We can't make any predictions. Now, situation B. You're playing that game over the summer. You're bored. You're drawing slips of paper to tell you where to go. Make sure you get your parents' permission. Don't wander off into the street. What do you think? You guys, I heard you guys talking. You got anything for me? I'm looking at you right there. Because I heard you guys talking. Thomas?
Sure, it's, equally likely because there are only 3 outcomes, and we know each of the 3 outcomes.
How's the choice being made? Is somebody thinking about, yeah, this is a random selection, so it is uniform because the selection is happening at random. We can infer that the chances of each individual outcome is 1/3. It's 1 outcome out of the 3. Random selection tells me it will be uniform distribution. So we'll pick up here tomorrow. We will do your problem solving lesson. And I'm debating when your mastery is going to be because we're going to lose our Stone Lab people. So I'm thinking it'll be early next week. So please make sure you try to plan accordingly and get your work done. Please bring in egg drop supplies. We will probably spend some time working on those on Thursday for those of you that are here. So please bring in egg drop supplies. We are likely going to, probably is a word that sucks, likely